Okay, so we're going to look at a 10 centimeter long capillary that is filled with water from 0 to 5 centimeters and D2O from 5 to 10 centimeters. We know the molecular weight of D2O is 20 grams per mole and the density is 1,110 kilograms per meter cubed. And the molecular weight of water is 18 grams per mole and the density is 1,000 kilograms per meter cubed. We have been told that at t equals 0.1 seconds, the max molar diffusion flux is 2.78 moles per meter squared times seconds. And when I look at that, I interpret that as since H2O is kind of flowing in the positive direction, or diffusing in the positive direction, the molar diffusion flux for water will be a positive 2.78, and since the D2O is diffusing in the negative direction, it has a molar diffusion flux of negative 2.78. Now this is a closed system and considered ideal. So that means that the sum of our molar diffusion fluxes will equal 0, and our overall molar flux will equal 0 since it is a closed system. Now the first question is asking us what is the overall mass flux corresponding to the max molar diffusion flux. And one step that we can take to get after this is finding out what the concentration of water is. So with that, the first thing that we're going to do is look at the concentration of the individual components. So we know that the concentration of component I is equal to the moles of component I over the total volume. And then we know that the moles of I is equal to the density of I, or the mass concentration of I, times the volume of I over the molecular weight of I. So with that, we can go ahead and calculate the moles of water. So the moles of water is equal to our 1,000 kilograms per meter cubed times some volume, which we don't necessarily know in the capillary of water, divided by 18 times 10 to the negative third kilograms per mole, so that our units cancel out. And that'll come out to be 55,555 times some volume of water moles of H2O. Now we can take this moles of water and we can plug it in to the concentration equation here. So the concentration of H2O is then equal to 55,555 times some volume of H2O moles divided by our total volume, which will end up being 2 times the volume of H2O, since there's 2 halves of our capillary and the H2O and D2O essentially have the same volume. And at the partition at 5 centimeters where the max molar diffusion flux is, that would be half of what the pure H2O concentration would be. So then from here, this would end up equaling our concentration of H2O, which would be 27,777 moles per meter cubed. Then we can go ahead and do the same thing for D2O as well. This concentration of D2O. Then our next step, in order to get towards the overall mass flux, we can go ahead and look at the equation for just molar flux. So that equation says that Ni is equal to Ji plus Ci, the concentration of I times the velocity of I. And as we said at the beginning, we know that the the overall molar flux for each component is going to be 0 since it's a closed system. So we can plug that in there, which will leave us with our molar diffusion flux equals the concentration of I times the velocity of I. And then we can rearrange this. So we solve for VI. So VI is equal to JI over CI. And then we can plug in our values for each. So the V of the velocity of water is equal to 2.78 moles per meter squared times seconds over the concentration, which again was 27,777 moles per meter cubed, which that'll come out to be 1.0008 times 10 to the negative 4 meters per second. And then we repeat that for D2O. So the velocity of D2O is equal to negative 2.78 moles per meter squared times second over 27,750 moles per meter cubed. And that'll come out to negative 1.0018 times 10 to the negative 4 meters per second. Oops, let me fix this. There we go. So then if we go ahead and we look at our equation for our overall mass flux, that's going to be equal to the overall mass concentration times the mass average velocity. So we can find this with the information that we're given. We need to find this with the new individual component velocities that we found. So we know that the mass average velocity is equal to the summation of the mass fraction of I times velocity of I from I equals 1 to n. And we know that the mass fraction is equal to the mass concentration of I over the total mass concentration, which we can break that down to each component. So the mass fraction of water is equal to 1,000 kilograms per meter cubed over 2,110 kilograms per meter cubed. That's just the sum of both densities. That's equal to 0.474. And then the mass concentration of D2O is equal to 1,110 kilograms per meter cubed over 2,110 kilograms per meter cubed. So that is equal to 0.526. So those are mass fractions for each component. And then if we want the summation of those times each individual velocities to get the mass average velocity, that would be 0.474 times 1.0008 times 10 to the negative 4 meters per second plus 0.526 times negative 1.0018 times 10 to the negative 4 meters per second. So our mass average velocity would equal negative 5.257 times 10 to the negative 6 meters per second. And then we can plug that into our equation for our overall mass flux. So our overall mass flux will be our overall mass concentration, which will at the partition, which will be 1,000 kilograms per meter cubed times some velocity of, or sorry, not velocity, some volume of water to give a mass of water at the partition, and then 1,110 kilograms per meter cubed times some volume of D2O to give the mass of D2O at the partition over the total volume, which is 2 times V, which essentially is both of these volumes together, times our negative 5.257 times 10 to the negative 6 meters per second, which will give us an overall mass flux of negative 5.546 times 10 to the negative third kilograms per meter squared times seconds. It's asking us to make an order of magnitude estimate for the max driving force for diffusion at t equals 0.1 seconds. Now, when I see this, I immediately think, how can we relate the diffusion estimate coefficient to the max driving force? So in this case, since they're both liquids and it's an ideal system, our diffusion coefficient is going to be equal to 10 to the negative 9th meter squared per second. And one way that we know we can relate the diffusion coefficient to the driving force while also using the molar diffusion flux was using Fick's law, which that is Ji, the molar diffusion flux, is equal to the negative of the overall concentration of the mixture times the diffusion coefficient times dxi dz, which this is the mole fraction gradient, which is the driving force for diffusion. So we can quickly rearrange this equation so we solve for the driving force. So the mole fraction gradient is equal to negative Ji over C D. And from the last problem, the last thing that we need to do is find out what the overall concentration is. So the overall concentration is just equal to the summation of the components' concentrations. So that's just equal to the concentration of water plus the concentration of D2O. So C is just equal to 27,777 moles per meter cubed plus 27,750 moles per meter cubed. So that'll be a total concentration of 27 moles per meter cubed. So then we can just plug all of our values into our driving force equation here. So our mole fraction gradient, or our driving force, is equal to the negative of our molar diffusion flux, 2.78 moles per meter squared times second, over our total concentration, which is 55,527 moles per meter cubed, times our diffusion coefficient, which is 10 to the negative 9th meters squared per second. So this will ultimately give us a overall driving force, or max driving force, of, we do want to take the absolute value of this because this is going to give us a negative number. So the absolute value of the maximum driving force is 50065 meters to the negative 1. That's our max driving force corresponding to our max molar diffusion flux. Alright, so the final question is asking us to sketch the following profiles at an initial time of t equals 0.1 seconds, an intermediate time of t equals 60 seconds, and a final time of t equals infinity seconds. So the first set of profiles is the mass concentration of water and the mass concentration of D2O over the change in position from 0 to 10 centimeters. So you can see from here that the initial mass concentration of water starts at the 1000 kgs, and then after the partition drops down to 0, and then the same for D2O, starts at the 1110 kilograms per meter cubed, and after the partition it drops down to 0. They drop down to 0 because at 0.1 seconds there has been essentially no time for diffusion, so the mass concentrations of each is essentially just their starting densities, as on either end of the capillary they're basically at full concentration. At t equals 60 seconds though, that's when both components have begun to diffuse to the opposite side, to the area of less concentration. So the profiles begin to flatten out, as the concentration for each begins to increase more on the other end of the capillary from where it began. And then at some infinite time, you'll see that the mass concentrations for both remain steadily constant, as they're pretty uniform through the entire capillary. And what you can notice is that this is essentially right around 500 kilograms per meter cubed. That is essentially half of what their starting mass concentration is, because now each component has occupied is occupying double the volume that it originally started in. Now going to take a look at the second set of profiles. So this is comparing the concentration of water and the concentration of D2O in moles per liter over the change in position through the capillary. So you can see that at the beginning, at t equals 0.1 seconds, on either end of the capillary, that is where we can consider each component in their pure state. So the pure concentration of each component is actually a little bit different than what we found before, which was their concentration at the partition, when the components began to mix and diffuse. So the pure concentrations of each can be found over here on the right. So that's actually just the mass concentration of that component divided by the molecular weight of that component. And these would be the pure concentrations of each component on either end of the capillary. So that's where our starting point is. And when they cross the partition, that is where their concentration that we found in problem 1 would be. So right around 27 moles per liter, or 27,000 moles per meter cubed. And then as we move into t equals 60 seconds, you can see, similar to how the mass concentration profiles began to narrow down, as they begin to diffuse farther through the capillary, the concentration on the opposite ends begins to increase, while the concentration on the starting ends begins to decrease, so kind of smoothing out that profile. And then ultimately at some infinite time, again, the concentrations for each component become constant throughout the capillary, pretty uniform. And again, that's right around where it would have been at the partition point at 5 centimeters initially. Alright, and the third set of profiles is comparing the molar diffusion flux for H2O and D2O over the change in position through the capillary. So we knew right off the bat that the max molar diffusion flux was 2.78. So since H2O was flowing in the positive direction, diffusing in the positive direction, it was a positive 2.78 moles per meter squared times seconds. And the D2O was diffusing in the negative direction, so it was a negative 2.78. And that was right at the partition at 0.1 seconds. So that is why it gives this profile for each component. And then as we move to 60, t equals 60 seconds, again, the max molar diffusion flux will decrease at the partition point, but increase as you go farther through the capillary, because the components have had more time to diffuse, so the concentrations are higher. The rate of diffusion increases on farther on either end of the capillary. And then ultimately, again, at some infinite time, remember that the summation of all the molar fluxes, all the molar diffusion fluxes, ultimately equals 0. So at some infinite time, there will be no more molar diffusion flux. So both profiles remain constant at 0. Now the last profile is just one individual profile curve, and that is the overall mass flux. So from the calculation we did in problem 1, we found out that the overall mass flux is right around negative 5.5. This should be times 10. Oops. This should be times 10 to negative 3. Right around negative 5.5 times 10 to the negative 3 kilograms meters squared times seconds. So right at 0.1 seconds, that's where our maximum or overall mass flux was at the partition at 5 centimeters in the capillary. As the time increases to t equals 60 seconds, again, the overall mass flux at the partition will decrease, just as the molar flux also decreases. And then eventually, at some infinite time, there will be no more mass flux. So the overall mass flux will just be a profile constant line at 0. So that is all 12 profiles, ranging from our comparisons of mass concentrations, molar concentrations, molar diffusion fluxes, and our overall mass flux.